So we have been talking a lot about X-ray diffraction, reciprocal space mapping, and even we talked a lot about kind of line profile analysis. What I am going to talk about is what is known as crystallographic texture. So texture is something that when you do an undergrad course in material science and engineering, this term you may or may not come across this term, right? Like texture, okay, I had no or very little idea about texture when I finished my undergrad studies, okay. It was during my postgraduate studies that I really looked at what is texture. But there is something that we really study as material scientists, and something that we really study as material scientists is microstructure. Okay, and if I were to ask you and put up a counter question like what is the what is a microstructure, you will say that it is the structure at the micron scale. And not only that, it gives you, the distribution, the type of phases, their size, shape, and distribution. That is what, is given over here. And there is a term which is given over here, which is orientation. So when I talk about orientations, orientation, it just happens like, you say North Pole is, rather your, which is that, pole star. Pole star or which star is that? Which points towards north, north star, right? So that way, so you orientation, is like always relative. Fine. So this orientation is what has something to do with crystallographic texture. And you should look, kind of keep in mind what I said. I called it crystallographic texture. Okay. So texture is nothing but preferred orientation. Okay. Preferred orientation. Preferred orientation of what? You can have morphological preferred orientation, or you can have crystallographic preferred orientation. So what I am going to talk about is crystallographic preferred orientation, or what is known as crystallographic texture. And the reason we are interested, why we are interested in microstructure? We are interested in microstructure because, if you go back to Professor Biswas's slide, he showed very nicely that, in one case you have these, these graphite needles, and in other case you have globular graphite. So see, just the size, shape, and morphology of your constituents of the microstructure can change your properties. Okay. So what I have chosen, that was a two-phase system. There was graphite and there was ferrite matrix. What I have shown over here is a single phase. In a single phase also you see that microstructure, the way we see is, you cut the sample, prepare it, and what we are looking at is actually a section of the microstructure, not really the 3 dimensions, because materials exist in 3 dimensions, right? So if you were to look, you get things like this, this is how your grains look like. What do these colors correspond to? That more Professor Shekhar will tell you. So I am not going to go into that in tomorrow's class. But what I am trying to tell you is that this is how your grains look like, okay, in 3 dimensions. So not only are the grains important, their boundaries are also important. The boundary between the grains is important. The size, shape, morphology, both as well as crystallography, all this is important. Why it is important is, if you look over here, this is a bad microstructure, but if any one of you have looked at fracture, if you take a tensile specimen and pull it, you can see interesting things like you see a crack which is growing, and then suddenly you see that the crack disappears, and then again the crack will appear. So crack hasn't disappeared, it has gone out of your view. Okay, so if you were to do 3D, you're going to see like this, so there is a crack which is going over here. Okay, so all this depends on property. So the property or the behavior of my individual grain as well as the grain boundaries is very, very important. So real microstructures are actually seen in 3D. So this is something which was obtained using microtomography in a synchrotron source, which is a very bright, 1,000 than a brighter suns, and it is intense also. So Professor Anand Subramaniam had mentioned that something that is bright may not be intense, but synchrotron is bright as well as intense. Okay, so this is where you see, this is obtained using a dual beam fib, where you can see that how the interface is looking, between this big grain, how actually the surface is, how the grain boundary is, it is not flat, it is a little stepped. So all these things are going to affect your properties. So what kind of properties are affected? Again, look at this. This is something that I did during my PhD days. Okay, and the reason I am showing all these colorful images is because I'll tell you the story about it, but just bear with me for some time. You see what is happening. I have this agglomerate of a polycrystal. This is a polycrystal, right? And as I deform, we did rolling, and this is on the transverse plane. You see different color grains. I won't talk about what the color corresponds to, but you see the way the blue color grain and the way this, this is what some pink color grain, right? A pinkish color grain. The way they are behaving is different. So that means for an externally imposed stimuli, right? Let it be deformation. Here I am applying stress, I am doing rolling. the behavior of individual grains is different. And why do I need to know the behavior of individual grains? Because the crystallography of each grain is different. And how does the polycrystal behave? The polycrystal is nothing but the average, right? Nothing but the average. So what I am trying to tell you that polycrystal comprises of millions of grains. Here I am looking at few tens of grains. But this is to tell you that for a given stimuli, I am just doing rolling 5%, 10%, 20%. You see how differently the grains behave. So to an externally imposed stimuli, your behavior is completely different at an individual level. But what I want to do, I don't want to predict my properties at a grain level. I want to predict my properties at the bulk level. So how am I going to get this? I am going to get this by integrating it, right? So I am giving you a bottom-up approach. What texture, the science of texture has actually gone not from bottom-up, from grain scale to the bulk scale, but it has gone the other way around. But I am putting the cart in front of the horse for the simple reason that this is very easy to visualize. Okay, so way back in 1970s, one of our, who is my academic grandfather, Professor Ray, when he joined IIT Kanpur as a professor and he started working on crystallographic texture, he went to one of the biggest steel manufacturers in India and he told that texture is very important for you. And he claims that, they called him that he is a madman. So if you catch hold of him, Professor Ray, he will tell you that they called him, he is a madman. By the time he retired, he had his, almost half of his graduate students working in the same company's R&D department. And after he retired, he was hired as a consultant by the same company. And the problem came because people were not able to appreciate what is crystallographic texture. And tomorrow, Professor Shashank Shekhar will talk about a technique which makes all these things possible. What all nice colorful images that that I am showing made these things possible, and that made people understand what is crystallographic texture. Okay, and why it is important. So remember, we can do very good research, but if we are not able, and in this case it was not because of someone not able to explain, but because there were no techniques. Okay, so it is very important, the presentation of your results, the way, so that the audience appreciates and understands it is very, very important. If you are not able to do that, there will be no takers for it. And this is applicable not just to individuals who are doing research, but also to a field in itself. Okay, so I have a simple request. If you just glance through papers in Nature and Science, which are the top-notch journals, just look at the images. And let me tell you, they are beautiful. Yes or no? And they convey a lot of science. So it's not just the way what kind of good research you do, it is also important to present it in a nice way. So in this case, the technique that Professor Shekhar will talk about tomorrow gives you a very nice way of, showing what all is happening. So it helps you visualize what is happening. So this is what we did. Then there is also an interesting thing where you can look at twinning. Okay, so you can go and look at twinning. This is again an in situ deformation study. Not only that, it's not just about deformation. You can also do and study recrystallization. So you see this what Professor Ungar just talked about. So these are all your twins. So you see the twins, and if you heat, the twins disappear.
Excuse me, sir.
Yes.
Sorry to interrupt, sir.
No, fine.
Sir, actually, I'm not getting understand by this texture, sir. How I can visualize? Understand?
I hope you get to know that by the end of this course. What I'm trying to tell you, you should tell me that in a polycrystalline material you see a grain boundary, right? There are different grains. Why there are different grains? Why there are different grains? What distinguishes one grain from another grain? Both the grains are of aluminium if you are looking at aluminium. Both the grains are of titanium if you are looking at titanium. Yeah, so that is what he's talking about, the stacking of unit cells. So if I look down the normal, which planes are stacked? So in case of cubic, that the plane normal and the direction, they are parallel to each other, right? So if I say HKL direction and I say HKL plane, that your HKL direction is normal to the HKL plane, yes, right? So that is changing. That is why you are getting a grain boundary. Yes. That is why you are getting a grain boundary. Okay, and that is what has been represented by different colors over here. So now, whenever you are kind of doing you are applying any external stimuli, be it stress or temperature, you get a change in microstructure. And if your microstructure changes, your property changes, right? And here it is done in a different way, but no one uses a cast material. I mean, there are few applications of cast material, engine blocks or your super alloys, but generally there is a whole set of thermomechanical treatment that is done. So when you are applying stress, you are heating, doing recrystallization, all your orientations are going to change. All the properties of the material are going to change. But What it shows, these are very fancy images. These are very good images. They tell you the micro mechanisms, but they don't tell you what is happening at a bulk level. So at a bulk level, what you are going to do? Bulk level, the only technique that can tell you, which is available in laboratory, is your humble X-ray diffractometer. Your humble X-ray diffractometer. So this is what really happens in a material, that when you deform, grains get elongated. What I am telling you that, hey, not all the grains get elongated the same way, depending on their orientation. Professor Unger mentioned that, if you take single crystal of copper along 100 and 111, the elastic moduli, is 3 times. The difference is 3 times. Okay. Now, I generally means except a few niche applications like superalloys, where you have a blade which is a single crystal, you generally tend to use polycrystalline material. So polycrystalline material is going to be an average. Okay. And now, if I am smart enough, I can go for, what kind of an average I can take. I can take simple average. I can take weighted average, right? So I can have an upper bound, so different averaging schemes. So which I want. So I want to exploit that. So to be able to exploit that, you should understand the concept of crystallographic texture. Okay. So where do these colors come from? So I have just written that what is crystallographic texture? It comes from the word texture, which essentially means the way things are woven in in fabrics, right? Like the kind of things, the kind of pattern you see over here is different. The kind of pattern you are having is different, right? So this is how. So this is for textile, but also the way your fabrics, rocks, or so. But this is all morphological texture. I am not talking about morphological texture. I am talking about crystallographic texture. And what do I mean by that? Okay, so this is like morphology. Look at this. Okay, so if you have a single orientation, if you take a single crystal, these are not really big grain boundaries. These are like the mosaic pattern, which Professor Garg talked about. Like mosaic pattern, there is a little bit of deviation, not perfect. Okay, so but the orientation overall is the same. It is the same. So it is a single crystal. If you go to a polycrystal, you have these grain boundaries, all different orientations, and all different orientations. If you take, then it is called a random polycrystal. Random. But you see what happens in reality. In reality, what happens is that there are certain orientations which are preferred. Okay, like see, all of you have come from different parts of India over here. Okay, and as such, the sheer probability of you to interact with some of your partners, like there is a big group from IIT Nagpur. So I can understand that the group from IIT Nagpur, any individual if you take from IIT Nagpur, he will be interacting most with people from IIT Nagpur, right? Right, Satish? But at the same time, then I can say that on an average, he is interacting same way with anyone outside, the subset outside IIT Nagpur, right? But if you look at it carefully, there will be at least one or few people, with whom he will be interacting more. That tends to happen, right? So he has some preference over interacting with someone. Similarly, in that group of IIT Nagpur also, 5-6 of you, Satish will be interacting with someone for a little longer. So there is always preference. So this is more in what is happening, in our, even in sociologically, because I believe humans and materials, they behave in the same way. Okay, so this is what happens. So there is a little bit of preferred orientation. Okay, so this is what we are talking about. So this is known as crystallographic texture. So here I have tried to show you what happens in 3D actually. Okay, so in 3D you can see that what different grains and different colors you are seeing. You see how the unit cells are stacked. To answer your question, so this is a schematic, because unit cell is of the order of angstrom. Okay, and your sample is of the order of millimeter to meters. So I have just blown the unit cell up to show you that how the grains are, how the unit cells are stacked in individual grains. And that when you are going to meet at the grain boundary, so the stacking sequence is different, and that is why you have a boundary where the sequence is changing, right? So this is the concept of polycrystalline material. What we want to do is to engineer the polycrystalline material in such a way that they behave, they give this anisotropy, because then from the same copper, the same copper, I can get higher strength if I want, or I can get lower strength if I want. Okay, so that is the whole idea. Like I'll give you a simple example. You have seen car body, right? See, when I want to make, if you go to, I worked in Tata Motors for 10 days. Okay, so I tell you, if you go to Tata Motors, they have these big blanking presses. Okay, so what they do is they have this rolled strip of steel, and you just punch it. You punch it, and then what comes out is your car door, and then they put in a lot of plastic and all goes in. But this is how make the car body. Now, when you are making this car body, you want your material to deform very easily. Yes or no? Because you want to give the shape. But the same material, once you have made your car, Someone is playing cricket, you don't want the same sheet to get deformed, like I throw a ball and then you get a dent in your car, right? Your neighbor's kid is playing and he hits a ball on your car, you get a dent. You don't want that. How do you achieve that? So isn't there a dichotomy? I want the material to be softer when I am giving it shape, but I want the same material to become strong enough so that some idiot who is playing cricket doesn't dent my car. Can I do it? Well, you can do that if you know crystallographic texture and physical metallurgy. Okay, so there is something known as paint, bake cycle and so on and so forth. You do hardening cycle and so on and so forth. So this is the entire philosophy that you want to engineer the properties. You need a handle to play with the properties. And if you understand crystallographic texture, see microstructure everyone knows, you play with the grain size or you induce some element or something, play with the chemistry, that you can do. So texture is also an important parameter, So you may not get 3 times change in strength or like elastic moduli, but you can get at least 50 to 60% change. That itself is quite good, right? So that is the entire idea of crystallographic texture. So what we will now go through is like, I'll just run through what are the important steps that we take to understand crystallographic texture. So I will not emphasize on, so this is what I showed you, different color corresponds to different orientations. You can see this hexagonal cell is there. You can see here the C-axis. So hexagonal cell is like this, so the C-axis is taller, the C-axis is taller, and see how it is oriented. So you can see C-axis going this way, this way, this way, all different possible orientations. And here what I have done is I have imparted a particular color to a grain. In what I showed you earlier is different, that we will try to understand what it is later. But here it is very simple. This is just like, you take world map, different countries are shown in different colors. Okay, and people have shown, mathematicians have shown that 5 colors are good enough. It comes from, what is the, like you don't need the nearest neighbor. Okay, so nearest neighbor should have different color. So if you apply that criteria, you need 5 different colors. But let's not talk about it. So this is all about, properties. So anything that is crystalline. I'm not going to run through the slides, but you can see there are some functional materials which are written over here, functional materials, and then I will show you something interesting. Your steel cup, this is a steel cup, or rather I should say aluminium cup, no, not steel cup, sorry, aluminium cup. The science of texture really came up for making, Coca-Cola cans, Coca-Cola and Pepsi cans. So if you look at the can, you have, how many of you are cola drinkers? Huh? So cola drinkers, there are 2 kinds of cola. One is normal cola and one is what? Huh? Diet Coke. Huh? So I know who is the cola drinker. You have seen the bottle of Diet Coke, which is lighter. Can you tell me what is the weight of the bottle? Have you ever wondered? Now see, it's like if I ask you what is my weight, give me a ballpark. I don't want you to tell me my weight till second decimal point. 50 kilo, 60 kilo, 80 kilo. Tell me, tick, A, B, C, D, none of the above. 60, yes. How did you tell that? It's a good guess. So, we have to learn to make educated guesses. You didn't say 50 because 50 is too low. You didn't say 80 because 80 is too high. Okay. So, that is what I want you to make. Like how much will be the weight? Ballpark. Kilogram, gram, milligram. Grams. Yeah. Tens of gram, hundreds of gram. Yeah, around tens of grams. Yes, 15, 16 gram. Now, how many of you have had that, what was that? Badam milk. Huh? That badam milk also used to come in the can. If you have ever touched that can, and what is the weight of that can? Go back to, means here they have it, you have that badam milk wala can, they try, that is a stupid design because the badam milk, all the dry fruits settle down, so that's a stupid design, it doesn't come out also. If you look at the weight of that can and look at the weight of the Diet Coke can, there is quite a bit of a difference. The difference is because, it's very simple, simple to understand that, the way you do it, you take a flat strip and then you just punch out, you punch out. So this is known as limiting drawing ratio, limiting drawing ratio. So can you imagine, you don't want if I take a very thin sheet, okay, and I try to punch something, the sheet is going to thin down. And if it thins down, it is going to fail. I don't want that. I don't want that. So what do? I start with a thicker sheet. Right? I take a thick sheet, chalo bhaiya thin hoga to bhi ye ho jayega. This is what that badam milk guy does. But the Coke guys have been doing this for the last almost 50 years. They have been doing this for the 50 years. So they know they can start with a very thin strip and they know texture. They know texture. So Hydro Aluminium, big company in Europe, they are the ones who are into this. And in US there is Alcoa. Or I probably, yeah, Alcoa is in US. Okay. So they make really thin strips and they just punch it. So they are smart people. They are not wasting your, wasting aluminum, and aluminum, it's a crime to waste aluminum, because the only way you can reclaim that aluminum is you have to again melt and, take it through the entire routes, and you are losing it, because, you put paint and you put stickers over it, Coke and this and that, nice color, you don't like that. So, and by the way, why I am talking about, why I am wasting my time talking about, Coke cans or beer cans is because, how many cans we use, the entire humanity uses. Forget about beer for the time being. Let's, on academic areas, we have to talk only about soft drinks. Those soft drinks kill more people than beer. Okay, so can you make a guess? No, in number. How many cans we must be consuming, humanity? Yeah, it's in billions. Yes, billions. And that is the problem with the Western world, Western model. What we have, we have a sustainable model. Okay, we look down upon our own culture. But the point is, ours is sustainable culture. Okay, so don't feel that the old-fashioned way. It's a waste. What is the point? Better than that, you go and start having nimbu pani rather than drinking cold drink. But Pepsi guys are smart. They also now sell nimbu pani, another in can. So that is economics. Okay, but can you imagine the implication on it? Huge. So one option is you have to make it continuously, and you don't like something like this. Why you don't like this? Because you have to chop off. These are known as ears because they look like our ears. You have to chop this off. Okay, so here I have shown you, this is nano indentation data, which is as good as looking at a single crystal. So here it is. This is for single crystal. So so you see 111 single crystal. So you see how much anisotropy is, right? Now see you can see the difference in the shape as well as the peak that you are having. Okay, same material, mind you, the material is not changed. 111, you are doing tension and compression. So different. The same material, cubic, we say that, bhaiya, you do tensile test or compression test, you will get the same yield strength. Not so for this material. Okay, not so for nickel titanium. This is one material which Professor Ungar also talked about. Not only that, if you take a polycrystal, you see the same thing in a polycrystal. Similar thing, similar anisotropy. In fact, anisotropy has increased. So polycrystals are very tricky material. They have distinct way. So they carry the footprint of your single crystal. So they carry the anisotropy of single crystal. Now, by knowing the knowledge of crystallographic texture, you can now exploit this. You can get more anisotropy or less anisotropy depending on what you want. So you can modulate this. It gives you an extra handle or an extra tool, and therefore crystallographic texture is very, very important. Okay, so now let us go back. So what I said, so whenever I am talking about crystallographic texture, I am talking about orientation. So orientation has to be relative, right? So whenever I tell you anything, so if I were to tell you where everyone is sitting, what is the easiest way of doing it? Yeah, reference point. So I'm going to fix my origin, right? I'm going to fix my origin. And once I fix my origin, I can tell you all the xy coordinates of each and every one of you, and then I can say that, this is empty, this is empty, this is empty, this xy is empty, and I can populate the entire matrix, right? But I have to have a frame of reference. So I have to fix my origin. So for this room, I can take my origin over here at that corner, or this corner, or this corner, that corner, anywhere. As such, I can take anywhere, right? But once I take it, everything is going to be defined. Okay, so this is something very important. You need a frame of reference. You need to fix your origin. Okay, so here it was about your individual points. So I defined an origin. But if I'm looking at orientation, I have to describe 3 set of axes, x, y, z. Okay, so that is very, very important. Not just saying that this is origin is not sufficient. How will I tell your x, y coordinates? I have to tell what is x, what is y, what is z. And I have to take nice orthogonal set of system because that helps me. Isn't it? I can choose anything as x, y, and z. But life becomes much easier if I take orthogonal, right? So there is a lot of symmetry and all involved. So you have to fix your frame of reference. That is very, very important. And how do you tell? So here, when you talk about material, remember, I am looking at unit cell on one hand, the unit cell orientation. And on the other hand, I am talking about, this is an engineering subject. So I am talking about the sample. So sample, it can be, a roll sheet can be very large, of the order of meters. And my crystal unit cell dimension is of the order of angstrom, right? So, I don't really care about what is the size. I care about the orientation. So, therefore, what is important for me is to fix 2 frame of references. For unit cell, the frame of reference is very easy. It is what? Crystallographic directions. So, you take what we take for simple lattice points, no, not lattice point, simple unit cell that we take, the smallest vectors. Okay, so we did that in Professor Rajesh Prasad's class. He told you for cubic you can have 1 0 0 0 1 0 0 0 1. These form a nice orthogonal system, right? 1 0 0 0 1 0 0 0 1. Fine. For just of texture has evolved for rolling. So for rolling also I can define in rolled sheet, if you see, that is also orthogonal, right? So you have three directions. One is the rolling direction, right? One is the normal direction. Normal direction is the direction along which you apply a load and kind of cause, apply stresses, and there is elongation along the rolling direction, right? So you have RD, you have ND, and the transverse direction. Okay, so these three are how they are orthogonal to each other. I care only about the axis. So I have these two frame of references. Okay, so what are those frame of references? One is RD, TD, ND, rolling direction, transverse direction, and normal direction. And I have, X, Y, Z, so which is 1 0 0 0 1 0 0 0 1. Remember, the lengths are different, the dimensions are different. This may be in meters, this is in angstrom. Okay, and then there is grain size also. Grain size is of the order of microns, tens of microns, and all. So understand the length scale issue. Okay, it's not about length scale. All I am dealing with is the angle. So I don't care if it is cubic, life is good, X, Y, Z normal. If it is orthorhombic, fine. If it is monoclinic or triclinic, forget monoclinic, triclinic. Even if it is hexagonal, there is a problem because your axis is not 90 degree. Life will become difficult. So in that case, what you do is something known as orthonormalization. So you understand, like you are normalizing it, and then there is this additional term ortho. Orthonormalization means that in HCP also you find out three axes which are normal to each other, because I don't really care about their lengths. All I care about is only their angle. Okay, so this is what you do. So now what I am having is a very simple problem. I have two frame of references. Okay, so now what I have written over here. So this is what? That is my sample. Okay, so this is my ND. Let me see it so that I don't mess up with this. So this is RD, and my goodness, TD. Right hand thumb rule. So if I want to call it 0 0 1, I think I have made a mistake. No, I haven't made a mistake. Good. 1 0 0 and 0 1 0. Okay, so I take the cross right hand thumb rule. 1 0 0 cross 0 1 0 gives me 0 0 1. Right up. So this is my what? This is sample frame of reference. This is sample frame. And this is my crystal frame. Frame of reference. Okay, let me write that also. And what is my texture? Texture is nothing but a relative orientation or the relation between the two, right? So here you see what you have over here. This ND-RD-TD can also be represented as X, Y, Z. So I have what is known as my sample frame of reference. Okay, and here I have my crystal frame of reference. And texture, by the way, so I'm going to call it, so coordinate system, right? So I call this CS, coordinate system for the sample, and I call this as CC, right? Which is the coordinate frame for my crystal, right? And the way I'm going to define texture is nothing but, well, I'll have to probably go on the other side, is nothing but, CC is equal to GCS. So this is my texture. This G tells me something about texture, or this is known as the orientation matrix. Texture in terms of the orientation matrix. Okay, because see, I have a bunch of directions over here. Okay, I have a bunch of directions. So 1 0 0 0 1 0 0 0 1. And now from here I want to go to another, the sample frame of reference. And you may feel that, array sample, why don't I have the sample frame of reference over here? Because these are passive rotations. Okay, so remember, there is something about active and passive rotations. Like I'll give you a simple example. If I give you a vector in xy coordinate and I ask you rotate the vector, that is active rotation, remember. But if I tell you no, don't rotate the vector, rotate the frame of reference. This is what we do in symmetry, that is passive rotation, right? So when you say that there is a fourfold, so when there is a fourfold, you are not rotating your vector. You are rotating your frame of reference. You are rotating your x and y axis about z. So these are passive rotations, and that's why I have CC is equal to GCS. So here, what is going to be my CC? CC is going to be crystal frame of reference, means I can write 1 0 0 0 1 0 0 0 1. You know, so 3 different directions. Okay, so let me write it easily for you. You know, so let me write it x, y, z. Small x, y, z is for 1 0 0 0 1 0 0 0 1. And CS is my NDRDTD. Let me write it capital X, capital Y, capital Z. Okay, these are all directions, but essentially I am writing this, and here I have G. So can anyone tell me what will be G? So it is like, you know, X, Y, Z to capital X, capital Y, capital Z. So yeah, transformation matrix, you are going to have all direction cosines. So direction cosine of what? Direction cosine of, you know, so G. Now let me go back over here. Okay, so G is going to be, you know, all our direction cosines, cos of, you know, so what do? You fix x over here, and then you say x and x, cosine of x and y, and cosine of x and z, right? And here what will you have? Cosine of y and x, cosine of y and y, okay, and cosine of y and z, and so on and so forth. So you see what you are having, this orientation what I talked about. Now I have put forward a mathematical way of representing it. This is very simple. This is just our transformation that we are doing. Only thing is this is passive. So it's like, you know, this very similar to what you do when you say, oh, I have a 4-fold along z axis. So what do? You have z. So if you have a 4-fold, see, you should be in a position to visualize. So I have x. So how do? X, y, z is coming out. I say I have a 4-fold. Okay, 4-fold. So that means if I rotate by 90 degrees, positive angles are anti-clockwise, right? So I have x over here, y over here. Let's rotate anti-clockwise. So how is clockwise? Clockwise is this way. I'm going to go the other way around, right? So what happens to my x? So this is x, this is y. If I go anti-clockwise, what happens? X becomes y and y becomes minus x. So now you apply similar, you know, cosine. So you know, so you will get what happens to z? Same is z remains same. So what you are going to get in the last matrix over here, the last thing that I have written, you are going to get 0 0 1, because angle between z, old z and new z is the same, but your x prime, your x prime, y prime, and z prime, okay, or z, that angle is always 90. So you're going to get 0 0, and the last point, when I say last, I mean that the third term which is over here, you know. So here what is that? So if I were to write, this is my z and x, z and y, and this is z and capital Z. So here instead of x, y, z, I am having z and z prime, right? So z and x, like for example I told you, this is 90, so cos of 90 is what? 0. So this is going to be 0 0, and cos of 0, because z and z prime are going to match, so it will be 1, right? And here you are going to have cos theta minus sin theta, cos theta, and here again you are going to have 0 0, right? So this is what we have been doing. So see, whenever you talk about orientation, it is a matrix. So see, orientation is not just like, okay, orientation kya hai bhaiya. No, orientation is a matrix. So you know, we have to learn a mathematical way of doing that. Okay, so that is what I have shown you over here. But you know, there is a very easy way of representing orientation. You know, so I will tell you. So this is what I told you, the G matrix and all, which is a mathematical way. But the simplest way of representing texture or, you know, orientation is to look at, you know, so this is my rolled, let's assume this is my rolled sheet. So if this is my rolled sheet, you know, this is my ND, this is my normal direction which is coming out, this is my rolled direction because this is longer, and this is my transverse direction, right? So if I say that, I just say, hey, come on, tell me which is the HKL plane, you know? If I take a normal to that HKL plane, that corresponds to ND. Simple question. That essentially means that tell me which is this plane crystallographically. If I go in a grain which is a single crystalline region, tell me which plane coincides with the ND plane. When I say ND plane, and if I am talking about cubic materials, you know that the normal to ND plane, okay, is ND, right? The normal direction HKL, what I told you. So which is matching. So I can write that HKL plane, right? So that will tell me which is my plane. And UVW is what? UVW is the direction which matches the rolling direction. Okay, which matches the rolling direction. So let me just go back and tell you, so if you were to go back, let us look at this one. So if you look at this image, which plane is lying in the ND plane? Yeah, 0, 0, 1, because see, now though I am talking about plane, I am essentially looking at direction because I have done orthonormalization. So you can always say 0, 0, 1. But sorry, the way I have written is, I write a plane. So I had written HKL UVW. And remember the way I wrote HKL UVW, as an orientation, how did I write HKL UVW? I wrote HKL UVW using a very nice way of, I used this bracket. Why did I use this bracket? Yeah, family. Why I use family? The reason I use family is for the simple reason that, it is my choice. There was this video of Deepika where what was my choice. Huh? So it's my choice. It's your choice to, Deepika Padukone, okay? So it's my choice to point out where is the origin. But that is not going to change the plane. If I say this is my origin or that is my origin, my one-on-one planes are not going to change. The family is going to change. Okay, but I don't know. One-on-one planes do not become like 1-1-0 planes if you change the frame of reference. One-on-one planes will still look like one-on-one planes. Because remember, your origin can be taken only at lattice points. You can't take origin at somewhere in the middle. You can't do that. Okay, so what is important is that I may take a particular family, a particular origin. So my plane will change. I may get 1-1-1 bar, what you are calling as 1-1-1, and what he may be calling as 1-1-1. Okay, so I may call it 1-1-1, you may call it 1-1-1 bar, someone may call it 1 bar 1 bar 1, but no one is going to call it 1, 2, 3. Right? So it is very important for me to put that bracket over there. And the reason I have put UVW is because it is along the RD. So now you tell me, what is the relationship between HKL and UVW? Yes, they are normal because the UVW direction is contained in the HKL plane. It is contained in the HKL plane. So remember, this orientation is known as a texture component. And in this component, an implicit assumption which many people tend to neglect, and that is what leads to all the confusion, is that your HU plus KV plus LW has to be 0. The direction has to be contained in the plane. People feel that, see, once I put direction, once I put the bracket, you tend to relax. Ki, "Arey bhaiya chalta hai." Okay, because all the family is taken. But what I'm trying to tell you, whatever, you should, whenever you represent this implicitly, you should make explicitly, it is implicitly assumed, but to make it explicit, make everyone understands, whatever means I can choose 1-1-1. So if the component is say something 1-1, 1-1-0, so I should not write something like 1-1-1, 1-1-0. This is wrong, or rather I won't say wrong, this is confusing. This is confusing because this is their dot product is not 0. But if I write it this way, and which is correct because remember, I'm just telling which is coinciding with ND and RD. So if I write instead of that 1 bar 0, right? This tells me very clearly that what different orientations. So what I can have something like, look, the change in bracket, I have changed the brackets now here. Okay, I can have something like this 1 bar 0. This is a particular plane, this is a particular direction. I can also have 1 bar 1, 1 0, and so on, and I can find different combinations. But I have told very explicitly that I can't take any 1-1-1 and all 1-1-0s. I have to ensure that whatever 1-1-1, whatever family of 1-1-1 I take, I have to choose only those 1-1-0s which give me that the dot product is 0. So this is something, and I don't blame anyone but people belonging to texture community. They are lazy. They don't do this, and that is what leads to all the confusion. So if you tell this very explicitly, it explicitly tells you that, the RD is contained in the ND plane. So this is something that you have to understand. So very simple, I'm just going back and seeing my unit cell and saying what is matching with this. Remember, this is in angstrom, this is in meters. And in between there you have, grain size and so on and so forth. So as your grain changes, this HKL UVW is going to change. Why we use X-ray, I showed you those colorful images. But those are very small. You have millions of grains. So if not millions, you want to, scan or interrogate at least a few thousand of grains. And that you can do only using X-ray diffraction. Okay.
This is known as texture component.
This is a texture component. One particular, a texture overall texture is nothing but like how many of them you are having, the frequency at which they are occurring, right? So even if you look at grain size is, you will give a number. That number is also not correct. You should give a mean and a standard deviation, right? So there is a distribution. Professor Ungar also talked about that. Hey, come on, you don't have grain size. You have a grain size distribution. Okay, so you calculate mean and sigma, and then you say that the grain size distribution is log normal. Okay, so when do you get log normal distribution? Again, you do that with X-ray. Why do you do that with X-ray? Because you are counting many grains. While if you are doing optical, even if the sincere most student will show a normal distribution and not log normal distribution. You know the reason why? Yeah, number is too less. If I were to calculate, all your height and weight, we'll see that we'll get a nice normal distribution. But if I were to calculate, average height of Indian males and females, I'm going to get a log normal distribution. Okay, so as your sample size increases, you tend towards a log normal distribution. Okay, so that you can do only in X-rays, because that is the correct representation, because the sample size is pretty large. Here I deal with averages because the sample size is very small. Okay, so that is the advantage of using X-rays. Okay, so this is the easiest way of representing texture. Another way of representing it, so here I have shown you, so here as I said, you measure all the angle, so easiest way of measuring is x, y, z, you measure angle, that G matrix I had written a cosine of angle between x and x prime, y and y prime, so on and so forth. So you measure all, so 9 angles to measure, quite a bit of a task, Here it's very easy for me to show you, but how to represent that, to measure all these things, it's going to take heck a lot of time. So a better way, a better mathematical way is by using what are known as Euler angles. So Euler angles are very, very sophisticated technique. So I have essentially two frame of references, x, y, z, and let me not call it capital X, y, z, let me call it x prime, y prime, z prime. I want to bring them into coincidence. So what in one case I was doing, I was saying, okay, bhaiya, x, y, z, x prime, y prime, z, let me calculate angle between x prime and x, x prime and y, x prime and z, angle between y prime and x, y prime and y, y prime and z, z prime and x, z prime and y, z prime and z, 9 angles. Instead of that, I want to do it only using 3 angles. And the way I do it is like this was proposed by Euler long back. This is French, so don't call it Euler. Okay. Similarly, Poisson's ratio. It is not Poisson's ratio. French, Poisson's. Okay, keep that in mind. So if you have these two, frame of references, what I do is, so I have ND, RD, TD, and I have 100, 010, and 001. So what I'm going to do is, the first rotation, I'm going to rotate about an angle phi 1. I rotate about an angle phi 1 about ND. About ND. So what if I'm going to rotate about ND, what is going to change? Nothing is going to happen to 100, 001 and 010, because I am not rotating that. If I rotate about ND, RD and TD are going to change. So RD, I say that RD goes to RD prime and TD goes to TD prime. But how am I rotating? I am rotating it in such a way that my RD prime, when I rotate about ND, RD and TD changes. So RD should go to RD prime, TD should go to TD prime. So I rotate in such a way that my RD prime is normal to the plane containing ND and 001. Okay, ND and 001. Why am I doing that? Because the second rotation that I'm going to do about an angle phi is about RD prime. Okay, so I hope you appreciate that if you look at any two directions, you can always define a plane that contains the two directions, right? You can do that. So now what I want to do is to bring my RD prime to such a location that it is normal to the plane containing ND and 001, right? So this I achieve by rotating about ND by phi 1 angle. Okay, so only one angle, right? Now the next rotation that I'm going to do is going to be along RD prime, So how do I rotate? So I rotate about an angle phi, okay, about an angle phi, so that my ND and 001 coincide. 001 coincide. So see, earlier I played a trick. What trick I played? I rotated about ND so that RD prime goes to a location such that your ND and 001 they lie in the same plane, and RD prime is normal to the plane. So similar to what I told you, that Z was coming out, I was rotating about Z, my X and my Y were going over here, right? So you do the same way. So once you do that, your second rotation is about RD prime. Okay, you rotate about RD prime by an angle phi so that your ND and 001 coincide, right? So now you have made one axis to coincide, right? Now the final rotation Now you go back to your ND, new ND, which is coinciding with your 0, 0, 1, right? So now when you rotate ND by just phi 2, you know that since it is an orthogonal frame of reference, now if you were to bring, and ND is already coinciding with 0, 0, 1. Now the moment you rotate, and bring RD into coincidence with 1, 0, 0, you obviously know that TD is also going to come into coincidence with 0, 1, 0, right? So just by defining three angles, I have told you, how to bring them into coincidence. So instead of measuring 9 angles, I am measuring only 3 angles, right? So this should be very clear. And for each and every angle that I have, I can write a rotation matrix, I can write, oh God, where did my rotation matrix go? So similar to the G matrix that we had written over here, cosine of angle between, right? X, Y, and Z. So the first G, what I call it as, my goodness, this is a bit pampered, today is not a good day. Okay, so the first rotation that I do is along, along ND, which is along the Z axis. So how the matrix is going to look like. G phi 1 is nothing but going to be cos phi 1 minus sin phi 1 0, sin phi 1 cos phi 1 0, 0, 0, 1, because ND is normal, right? The second one is tricky. Second one I am doing along RD. So instead of my third parameter being this, I was having 0, 0, 1. Instead of the last row being 0, 0, 1, the first row is going to be 0, 0, 1. Okay, and then again when I come to the third one, it is going to be the similar. So then what I have, this G matrix that I have written over there, that G will be nothing but G phi 1 into G phi 2 and G phi 3, because it is like 3 systematic rotations, right? So it's a very elegant way of representing orientation. So now any orientation that I have can be represented, just a minute, can be represented in terms of these 3 angles, phi 1, phi and phi 2. Okay, so each and every orientation, instead of writing HKL, UVW and confusing you with the brackets and then saying that you change the orientation and all, for all different things you are going to get a distinct phi 1, phi 2. So that is an easier way of storing my information, right? So from 9 angles I have come down to only 3 angles. So yeah, please.
Sir, G is the product of the
all the 3 rotation matrices, because that is like you are doing one rotation followed with another rotation with another rotation. So it's like first transformation, then you transform another transformation, and then you want to, this is simple matrix algebra.
Sir, for fast matrix, the last row is
0, 0, 1. Yeah, because you are rotating along ND, yes, right? The second case you are rotating about RD, which is your x-axis, right? So the first one will be x will be 1, because x is not changing, right? You rotate about something, the angle between the old and the new is 0 degree. Come on, if I rotate about Z, yes, Z and Z prime are the same. It's not going anywhere. So now when I rotate about RD, it's going to be 1, 0, 0. Not here, I had 0, 0, 1 over here, right? So I'll share the text with you guys, okay? So this is a much easier way of representing orientation, okay? So this is something that you should keep in mind. I have gotten rid of the maths because that maths seems to, kind of confuse people, but I will add that slide, before I share it with you. So these 3 matrices are there. There are other different, complicated ways. I have a separate presentation on Roderick-Frank space and quaternions. At least on quaternions I have one, but I won't share it with you. So this is like, if you have 2 different orientations, it essentially says that you can always find a unique axis. Instead of rotating about 3 different angles and all, you can find a unique axis about which if you rotate, you can bring the 2 crystal or 2 orientations or 2 frame of references into coincidence. But this is a little tricky. Okay, this is a little tricky, so let's not do it. Generally, let us stick to Euler angles. Okay, so you can imagine, like that those angles and the directions can get a little complicated. Okay, but these are also better ways of representing texture. Okay, so how do you I have measured texture, but to represent, I need to read texture so that I can tell you. And that is where, you have these, what are known as pole figures, orientation distribution functions, and inverse pole figures. And these are complicated. And for this, you got to know the stereography very well. I will touch upon it, but this is something that you have to develop. We have Professor Suresh here from IIT Roorkee, and he will also tell you that it takes us a few years to understand it. I'm still in the process of understanding or to read pole figures and all. Okay, so you have to develop, and for that, you really have to understand stereographic projection. Similarly for Euler angles, So, but remember, what is the underlying principle? The underlying principle is symmetry. So your symmetry of your crystal, gets reflected everywhere. So we have to go back. See, this question you should ask, stereographic projection. In BTech undergrad, it is covered. Why it is covered? And then you just forget it, right? You just forget, यार यहाँ stereographic projection पढ़ लिया भैया, 100 standard stereogram निकालना है, and after that, I tell my undergrads that it's like semester खत्म दुकान बंद. They forget it, so by the time they come to me, so third semester I teach them stereographic projection in mechanical behavior, okay, because they don't know what is single slip, cross slip, and so on and so forth. So, but when I again teach this course in the 8th semester, they have forgotten. So we can't do that. And if you ask this question that why stereographic projection is taught, you should do, it has tremendous implications. And that is what I will try to show you. So what I'm going to do is I'm going to give you a glimpse of things, but if you really want to understand, you have to go back and read it so that you can appreciate it. So we'll talk about pole orientation distribution functions and inverse pole figures in a bit of detail. So what I'm going to do is I'm just going to show you this is how a pole figure looks like. So pole figure is essentially a radial plot. So when you talk about plot, you can have just 1D, like 2 theta versus intensity is a simple 1D plot. So you have one variable over here and x and y. Here you have two variables over here. So you can have one thing along x, one thing along y, and what is coming out is an intensity, right? So you see, what you see over here is your, so what is fixed over here? So it is your RD, TD, and this is your ND. So what you are fixing is your sample frame. You are fixing your sample frame, and what you are looking at over here, so see 111 and 200. So these are what are known as projections. Pole figures are nothing but projections. They are like stereographic projection. So in your engineering drawing, everyone has done a course on engineering drawing. So in engineering drawing, what is the favorite question? They give you front view, side view, top view, and then they ask you to construct the isometric view. Okay, so does the object change? It's the same object. It's only your view that is changing. But now you see, now you have to keep one thing in mind. Here you are not really working in the Cartesian coordinates. You are working in the orientation. So these are like spherical coordinates. So life becomes a little difficult. But this is from the same material. So both of them are giving you more or less the same information. These are, kind of additional pole figures. So these are the simulated pole figures. So they are giving you the same information. So it's like the same object can have a different front view and a different side view. The object is not changing. The object is not changing. So this is something that you have to keep in mind. So if you take a pole, if you were to measure a pole figure from the material, it is not like you may get slightly different information, but it's the same thing. Only thing is your way, your view, your view or your projection, the direction of projection or your axis of projection is changing. So it is just like, in fact, a better example is that of an elephant. And the blind man trying to describe what is an elephant. Okay, so what, someone touches his trunk, the elephant's trunk, someone touches the leg, someone touches the tail and says that, the elephant is like this, like a rope or like a pillar and so on and so forth. But the complete picture is, you have to take information from all of them. So here you are blinded, not because of the blindfold, but there are some experimental limitations. So everything, so you take everything from everyone, what all little information you can get, then you combine it in an intelligent way, like you do in your engineering metallurgy class, in engineering drawing class. You look at different views, and from that you construct the isometric view, which tells you exactly what is happening. So something similar we have to do. So these are the pole figures. Stereographic projection, everyone is an expert in stereographic projection by now. So like what you have this over here, the crystal over here, and you draw the normals. They lie on the sphere, right? So this way, if you change the orientation, so you see the cube is at the center, but I can tilt the cube, I can twist the cube, I can, rotate it by different angles and all. This is very similar to what I told you that, how my orientation is changing. If I do that, what happens? See over here how the 100s change. These are the same things. Here they are behaving like nice boys. Here you see they are changing. So here I have put a sample, and instead of fixing 100010, I have fixed RD, ND, TD, and I am seeing like how the orientation is, see, which is drawn over here. So you can see this is just a stereograph. So this is my ND, RD, TD circle or the sphere, and here you see this is my crystal is. So then I project crystal. So on my sample frame of reference, I am projecting the crystal, right? So see what I am doing, see that is the beauty of having orthogonal frame of reference. I draw this ND, RD, TD, right? So now if I had an orientation which is like this, where is it? Which is like this. So what would have happened? ND is matching with 001, right? So what I would have got over here? I would have got something similar, you know, first one, right? But here you see, here it is different. The orientation is different. I have not drawn the bars, but the bars will lie behind, you know, that if 0, 0, 1 is lying here, this will lie at the back, you know, you just have to take it through the center. Okay, so this is essentially, so what is fixed here? In pole figures, your sample frame is fixed. And then with respect to sample, I am plotting my crystal. Okay, you do exactly the opposite. Okay, so this is stereographic projection, how it is constructed. Again, please refer to quality. If you want to do anything in texture, you have to know what is stereographic projection. You have to know what is symmetry. Okay, these things you have to really go through. So what I am trying to show you is the original case that I showed you. That, you know, just a simple, so if this is, let's assume this is the cube and this cube is lying over here on your rolled plate, you get something like this, okay? And what you will end up seeing is that, you know, these are different stereographic projection. I have shown you the orientation in terms of HK, UVW. Note that HU plus KV plus LW is equal to 0, right? Always, okay? So what I do, it's the same orientation. You see, if I look at 1, 0, 0, so if I say that no, I want to look only at 1, 0, 0. So how they will look like, you know, in 2D, one at the center, there is one at the back which you can't see, and the two at the top. But now instead of looking at 1, 0, 0, if I say, hey, no, I want to look at 1, 1, 0, orientation is not changing. Only my frame of reference is changing. So these three tell me the same information. That my, you know, this is my NDRDTD and this is how my unit cell is. It is not, orientation is not changing. It is just my view. It is just my view which is changing. Okay, whether I am looking front on, side on, or crystallographically whether I am looking along the 1, 0, 0 or I am looking along 1, 1, 0. So very simple, you know, all of you know how to do measurement of angles between two crystallographic planes. What is the formula? Cos theta is equal to? Yes. So now you know that, you know, in this case, what is happening in this case? 1, 0, 0 and ND are coinciding and 0, 0, 1 and RD are coinciding, right? You know that. Fine. So now here I am, what I am saying, hey, now I am not looking at 1, 0, 0. I am looking at 1, 0, 1. 1, 0, 1 pole figure means I am looking at 1, 0, 1 poles. So what is the angle between 1, 0, 1 and 1, 0, 0? Yeah, 1, 0, 0. 90. Yes, see, multiplicity is there. So yes, it is 90. So now this is, so when I say 1, 0, 1 means my center is, forget about what I have written. 1, 0, 1 pole figure means at the center it should be 1, 0, 1. So 90. So can you tell me what is the locus of all the points from the center which is at which are at 90 degree? No, it won't be a square. If I asked you locus of point at a distance of, you know, 10 meters from where I am, it's going to be a circle in 2D. No, not ellipse. How can it be an ellipse? Come on, why it will be an ellipse? That's a great circle. Okay, but that is wrong. Ellipse, it cannot be an ellipse. It's going to be a circle. See, if I'm standing here, if I say 10 meters, what are you going to do? This is my center. Okay, you draw a circle. In 3D, it's going to be a sphere, right? But these are 2D projections, right? So you see, your projection is 90 degrees. So, you know, everywhere inside, you know, everywhere, that outer circle, everywhere you can have. But you don't have points at all the orientations because, you know, there is another criteria. Your 0, 0, 1. Right. So what is the possible angle? 90. Is 90 degree the only possible angle, or there is some other possibility? Look at all the possibilities, you know. So if I ask you in the family, what is the angular relationship between 1, 0, 0, family, not one specific I am giving you, okay, family of 1, 0, 0 and 1, 0, 1. 90 is one answer. 270 I want, okay, fine. 270 is what? 2 pi minus pi by 2. So I don't care, that's the same. Something else? Come on, you guys. See, that's why, you know, when I was undergrad and they used to make us calculate angles between, I said, kya bakwas hai yaar, why they are making us do that? It is important here. It should be on your fingertips. Array? 1, 0, 0 and 1, 1, 0. 360 is redundant. 360 is certainly not correct also. Array? Look at the family 1, 0, 0 and 1, 0, 1. 45 degree. So you have also locus of 45 degrees. Right? So that's why you have these points. So you see, the angle between 1, 1, 0 and 1, 0, 0. So see, if my 1, 0, 0 is pointing at the center, okay, it is coming out. So I am asking, where is my 1, 0, 1? So it can be either at 45 degrees or it can be at 90 degrees. That is what you see over here. You see, this distance is, this is at 45 degree, this is 90 degree. How it comes there, you know, you have to really work with stereographic projects. So I'm not going to cover that, but I'm going to tell you that you are seeing the same presentation. It's not that the orientation has changed. Okay, I just asked you, I look at 100. So you know when 100 is coming out, I see 100 at the center. But if I say, okay, now I'm not looking at 100, I'm looking at 101. The orientation has not changed. So if 100 is over at the center, where is 101 going to be? It is going to be either at 45 degrees or at 90 degrees. That is what you see in the second graph. Now look at the third graph, the third figure over there, 1 on 1. What is the angle between 100 and 111? Calculate. 1 over root 3. Cos inverse of 1 over root 3. What is that? No. Around 54 degrees. Huh? No. 71. Who's good at calculations? Yeah, it should be around 70. Around 70 degrees, right? So you see, that is what you are seeing over there. Okay, you don't see anything at the periphery. Your orientation has not changed. Only instead of looking at 100, now I am saying, hey, I'm not looking at, now looking at 111 orientation. So when you go from figure 1 to figure 2 to figure 3, your orientation is not changing. Only your frame of reference. So instead of looking at 100 in the first figure, you are looking at 101. So you see that there you will find some intensities at 45 degrees and 90 degree. Orientation has not changed. 100 is not changing. No, but now in the second figure I am not looking at 100. I am looking at 101. Okay, and in the third case I am looking at 111. So it's only your view that is changing. The object is not changing. Okay, so this is where all your crystallographic planes, directions and their angles is important. Okay, so this is what I have shown you over here. Let's not go in details of this. But what really is important is like there is something known as inverse pole figure. I told you for rolling. For rolling, there is ND and RD. But some of you must be doing thin film deposition. Can you define two angles over there? Or rather two directions over there? No. There you can define only one direction. Like what is your growth direction? In which direction your film is growing? Or if I am doing wire drawing, I can define only one direction. So then then this breaks down. I don't need orthogonal frame of reference. So now what I'm going to do is, instead of defining a sample frame of reference, instead of defining orientations in terms of sample frame of reference, I'm going to describe them in terms of crystal frame of reference. And then I say, okay, tell me what is the growth direction. Tell me what is the growth direction. And I plot that growth direction on this triangle. Now you tell me why I have taken this triangle. I had this 100 standard stereogram over here. I have this 100 standard stereogram over here. This is simple, okay. Yeah, this is my 100 standard stereogram. Everyone understands this? Okay, so those lines are not clear, but there is also a line joining 1 bar 0 and 1 0 1. There is a straight line. So if you were to draw these lines, and you look at one quadrant, just look at one quadrant. If you were to draw this line between 0 0 1 and 1 bar 0, how many closest, smallest triangles you are going to have? These are triangle, the triangle has 3 edges, right? These are in normal system, Cartesian system. These are curvilinear, okay? These are spherical coordinate, not curvilinear, these are spherical. So these are known as spherical triangles. So how many such triangles you have? In one quadrant? 6. Everyone has seen that or not? Everyone can see that, one triangle here, so and what is the edge of that triangle? See 0 0 1, 0 1 1 bar 1, right? Then 0 0 1, 1 bar 1, 1 0 1. 1 0 1, 1 bar 1, 1 0 0. Again 1 0 0, 1 bar 0, 1 bar 1. 1 bar 1 bar 1, 1 bar 0, 0 1 bar 0. 0 1 bar 0, 0 1 bar 1, 1 bar 1. For everyone, each and every one of them, what you have is the family, right? And they are crystallographically similar. You see 1 0 0, 1 1 0, 1 1 1, right? So this is occurring. So overall, how many such triangles you have? In one quadrant, if there are 6, 24, right? But in stereographic projection, what you are projecting, are you projecting all the orientations of the sphere, or you are only in one? Only in one hemisphere. So if in one hemisphere there are 24, then in the entire sphere, how many are there? 48, right? So you are just looking at half, okay? But if you want to really reduce them, all I need to show is this one triangle. This is the fundamental zone. This is the smallest representative zone. Take any HKL family, you will find that orientation over here. Like if I were to ask you, where is 112? So 112 will lie between 111 and 100. So when I say 112, it's the family. So I may even get 211. Okay? Or if I were to ask you, where is 211? So you have to be smart. You say, hey, 2, 1, 1 is like 1, 1, 2 family. So here I can easily get 1, 1, 2. Add this, oh, this is 1 bar 1, 1, which is not really good, you know. So you can add these two up and you will get say something like 2, 1, 1. Okay, it should not be 1 bar 1, 1. That's a little complicated. So this is how you can add. So this is the fundamental zone, you know. This is the fundamental zone that you are having. So use that and plot your sample direction. So whether it is growth direction or your wire drawing direction. So this is also one way of representing texture when only one direction is important. Only one direction is important. I can also show it in a nice circular way, but the problem is if I do that, I'll come to Euler space later. But if I do that, I get this. This is useless, right? It's like unnecessary information that I'm having. I can compress this information because you know there is axial symmetry. Okay, when you are doing growth, you are assuming that there is axial symmetry. Everything is symmetric along the axis, right? So this is unnecessarily showing all the information. So therefore, I don't show that. I show this. Okay, so this is my inverse pole figure. So the Euler angles are something like, you know, I told you that there are 3, phi 1, phi 2. You know, so these are Bunge and Williams notation. Let's not go into that. But what I can do is I can plot them in 3D space. I can say phi 1, phi 2, like just like I said x, y, z. In x, y, z, I plot my points. I do it that way, and then I do nice smoothing and all. So each point corresponds to a particular HKL UVW and a particular orientation, which can be converted to phi 1, phi 2. And notice one thing over here. Here, what do I have? Which brackets I am having? Do I have a family? No, I have a specific component. I have a specific component. So that is the beauty of Euler space. It is more populated. It is more populated. It has more details. Okay, but it makes life difficult. Okay, so this is how your Euler angle, Euler space looks like, and ODF section. So this is a very nice analogy that I have. You know, when I talk about, you know, stereographic projections and all, you know, where does the pole lie? How do you define a plane? Remember, we are defining a plane and a direction. HKL UVW, right? HKL UVW. So it's not just my plane which is important, but plane that tells me the ND plane, and RD tells me the rolling direction, how it is coinciding. So you know that the construction of stereographic projection, you have unit cell, you have all these planes, their plane normals intersect on the sphere of, on the surface of the sphere. Okay, so if I were to ask you, what is the radius of the surface of the sphere? I am sorry, the area of the surface of a sphere? 4 pi r square, right? So 4 pi r square, and this is generally a unit sphere. So if you look at the angular range that you have, it is 4 pi. 4 pi, forget about r square, okay, unit sphere, you know, reference sphere, you take unit sphere. So you can have the angular space that is available to you is 4 pi. So this is the analogy is similar that, you know, if you are in a ship or boat and you are going somewhere on earth, you know, somewhere in the Pacific Ocean. So I can always tell you what is your longitude and latitude. That will tell me where the boat is lying, right? Okay, but if you are not lucky as Columbus, so Columbus wanted to come to India and he decided to go the other way around. You know, his idea, he knew this, he knew stereographic projections, okay, so he went the other way around and he discovered America, isn't it? That everyone knows. So I don't just have to tell you that where you are lying, but also which way you are going, isn't it? So in good old days, you know, there were no powered, you know, engine powered, your boats. So what you used to use is a sail. No, not sail means nowadays you guys don't know what is sail. That yacht starts there, no? So they have these sail. So boat, and there is this sail which is at the top. So I have to tell you what is the direction of my sail also. So whether I am going northward or southward or eastward or westward, I need to tell you that. So HKL tells me, you know, which is the plane, and UVW tells me whether I am going to be lucky as Columbus and discover America or go to India, right? So HKL UVW. So the overall combination that you have, 4 pi is the opportunity, is like the entire space or the area on which you can lie, 4 pi r square, integrated 4 pi. And then how much feasibility I have? I can go top, left, right, bottom. I have the entire 2 pi possibility, right? So you see, I am here. I can point and start walking in any of the direction. I have complete 360-degree freedom, right? So 4 pi to tell me where I am standing, and 2 pi to tell you which way I am going. So overall your orientation space is 4 pi into 2 pi. That is 8 pi square. You can integrate it and all. I have shown you those 3 equations. Okay, those equations. There is a triple volume integral over there. But the physical significance of it is, you know, where am I? My longitude, latitude. That is important. Okay, how I am telling it in terms of 5 and 5, that's a different story. But not just that where I am. You can also tell what is my longitude and latitude. But you also have to tell me whether I am looking at north, south, east, west. So this is the complete information. So the complete information, the entire volume of the Euler space, or the entire space that you can canvas. Like volume, when I say volume, I mean like, come on, all of us have to be in this room. You can't go beyond this room. Because if the lecture is here, I mean, some of you are spending more time in the launch, that's a different story, you know. But I mean, like, you know, we have to be here. So the overall possibility or overall scope that we are having is the volume of this room. Okay. Similarly, for these guys, the entire volume or entire probability or the entire Euler space that you are having is 8 pi square. Okay. And then obviously as the symmetry comes in, you can reduce it and so on and so forth. But this you keep in mind. Now what I'm going to do is I'm going to tell you how I have talked. Yeah, angularity, like see where I'm going. I can go either this way, complete, you know, 0 to 2 pi. This is my 0 to 2 pi, how I'm going, this way, that way. So if I walk this way, I will go for the lunch. If I go this way, well, I will end up nowhere. Isn't it? So that's important. So that's what we have to, all of us have to walk this way for lunch. If you go this way, there is no lunch. Isn't it? So that's important. It's important, right? So now what I'm going to do is I'm going to skip a few slides. These are very interesting things. So this is how pole figures look like. So once you get these simple orientations, you know, you draw nice contour lines and so on and so forth. An important thing is not only is your crystal symmetry important, but also sample symmetry important. Why I am saying, because symmetry is not just of crystal, cubic, hexagonal is different, but even sample has a symmetry. Like when you do rolling. Rolling, you know that there is orthogonal symmetry, right? So there is a twofold there. Twofold, like you can't tell me the difference between, you know, this is positive rolling direction and this is negative rolling direction. Can you tell the difference? No. There is difference between, there is no fourfold here. Because if you were to rotate by 90 degrees, RD and TD is different. But plus RD and minus RD, there is no difference, right? This is clear. So there is a twofold here. So that symmetry gets reflected. You see, here each and every quadrant looks the same. Yes or no? Or like it's the mirror image. I should not say it's the same, but you know, it's quite similar, right? But there are processes. Anyone works on ECAP over here? Equal channel angular pressing or asymmetric rolling, triaxial forging. Professor Jayaganthan student, anyone? So triaxial forging, you are breaking the symmetry. Every time, see compression is again, compression you can define only one axis. But now what you are doing is, in triaxial compression what you do is you compress along X, you compress along Y, you compress along Z. So every time you are changing your direction. So you are breaking the symmetry. Okay. So this is very, very important, and there is a fundamental reason why we are doing that is a SPD process, isn't it? So this is important, but you know, let's not go into it. What I'm going to do you is like the analysis part and all is too involved. I'll tell you how we mathematically do it, and remember, this is also important, that whatever process you want to do, you are going to get crystallographic texture, and that is why Professor Ungar was also mentioning that texture is not an exception, it is a rule, it is always present. It's only that the limitation is on us, we don't appreciate texture, and this is because we were not able to understand it. Okay, but now with these sophisticated tools like electron backscatter diffraction, about which Professor Shekhar is going to talk tomorrow, you will be able to visualize it. What all I told you is a little difficult. You know, I am showing you these images and saying that, oh, there is texture. You know, to read this, you know, these kind of images, or to read, you know, these kind of images on one hand, and to see those my colorful images, you know. They say a picture is worth 1,000 words, or to see these kind of images. Which is attractive, you tell me? Obviously this is attractive, right? You appreciate it more. The deformation, tuning is happening, then recrystallization, the orientation is changing. This is attractive. Picture is worth 1,000 words, certainly. But this is not attractive, isn't it? I know that. But this is useful. This is useful. It's not like, you know, always something that is attractive is good. This is useful. Because what all I showed you, those colorful images don't tell you much about what is going to happen at a bulk level. Okay, but this does tell you. This does tell you. So what I have to do? I have to use these two techniques together. Okay, now I'll tell you how to determine this. And as I said, I am looking at, you know, I have to use some filter. How to do the calculations and all is not important. Okay, whatever you do, whether it is solidification, thin film deposition, deformation, recrystallization, phase transformation, annealing, you know, anything that involves crystallography, you are going to get texture. Okay, whatever you do, but depending on that, you may have one or two different frame of reference. Phase transformation, these are chapters in itself, all these are chapters in itself, and it's not like you can run a 5-day course only on crystallographic texture. But what I want to say is that you do any thermomechanical processing, solidification, anything that you do, you are going to get crystallographic texture.
Sir, in solidification also there is 3 directions.
Why 3 directions?
Sir, if you take the
No. Think of it in a proper way. What is the most important thing in solidification? There is one direction which is important. Growth direction, or which is opposite to that of your heat flow direction. Okay, that is important. No, threefold, Papa, that is like your mold is the mold shape. No, you can extract heat from 3 or 4 directions. That is your choice. Okay, but ultimately you are going to look, so what happens? You get a chill zone, then you are going to get a columnar zone. Okay, so see, what you are confusing it is with just the morphology. But yeah, instead of looking at this way, either से दिखूंगा. Ultimately, it is the same, ना? Oh, क्या यार ये sample को ऐसा दिखूंगा. One day I wrote sample like this, another day I wrote sample like this. Is it going to change? If I look at this wall and if I look at the bottom wall, okay, here I have columnar grain. The chill zone, then columnar grains, then equiax zones. They are in horizontal direction. Here they are in vertical direction. But come on, that's because your wall. But the heat growth direction, if you look with respect to your heat growth direction, it's the same. तो बस morphology change हो गया भैया. But keep that in mind. This mistake people make, because when you are doing any kind of, whether you are doing microscopy or X-ray diffraction, what people tend to do, आज सोमवार है, सोमवार को sample ऐसा डालेंगे, मंगलवार को ऐसा रखेंगे. वो नहीं. You have to load the sample exactly the same way, whether you are doing simple X-ray diffraction or you are doing, SEM or whatever, even optical microscopy. So these are small things because the changes are subtle. Okay, so I'll just spend some time to tell you how exactly. I'm not going to tell you, these are beautiful microstructures. Even in optical you can see this difference in structure or orientation. So this is my favorite. This is chiral pneumatic structure. This again, what Professor Rajesh Prasad talked about. This is magnesium, very nice image. Different orientations I'm not going to talk about. But what I'm going to do is I'm going to exploit Bragg's law. So here my filter is what? I told you that I'm going to look at only 100 or 110 planes. Okay, so let's not go into it. This is a stick pattern. Okay, so you did structure factor calculation in the 2nd class by Rajesh Prasad sir, right? And we saw that this is how the stick pattern should look like. The intensity decreases, right? There is no broadening and all. But if you look at this, what do you see? The peaks have become broadened and all. And Professor Ungar is trying to explain us why the peaks are becoming broader and all. But also notice one thing. In this case, the intensity ratios have changed. I'm not saying intensity has changed. I'm saying intensity ratio. So what I'm saying that I111 by I200. This is FCC. FCC 3, 4, 8, 11, 12, 16. So 3, 4, 2 peaks are closer, 8 is far off. 11, 12 closer, this is nanonickel only. Okay, so you see what is happening. Nickel, nanonickel. So it is broad, the peak ratios have changed. So tell me, what is happening to the frequency here? Why the intensity of 200 peaks is high? 200 are more, their frequency is more. So this is the first indication of texture. This is the first indication of texture because there is a deviation. I should have got like 111, then 200 and it is decreasing. But how do I get it? I get, come on, like why 200 is going up? That means, and this is like what you do, right? Like iron, you electrodeposit iron, then you look on the, the side facing cathode and the side not facing cathode, right? Both ways it shows like this, right? So it tells me what is my growth direction. So just by looking at this, you can say, hey, my growth direction is 200. He is doing electrodeposition, atom by atom deposition. Okay, you can just look at this and say, hey, there is 200, right? And you have looked at the broadening and all, but just by looking at X-ray peak. This may change, if one day you try doing that, keep sample at 0 degree, 5 degree, 10 degree, your peak ratios will also change. So that's why it is very important to load your samples in the same way. This I have taken hexagonal material, titanium, and you see I do XRD on different faces. The top face, this is like NDRDTD I do on top faces. You see these two are similar, but look at this one. Same material, instead of loading the sample this way, that way, I have loaded, I am looking at 3 different faces. The top face, the side face, and this is the edge face, right? Now this is very clear over here, but we cut sample into small pieces and then we do. So that's why I'm saying that you have to be smart enough. Every sample has to be cut in the same way. Okay, we tend to cut ki kya hai, copper to copper hi hai bhaiya. No, copper to copper nahi hai bhaiya. There is a difference on which face you are seeing. They have to be the same throughout your study. And then you are scratching your head and your advisor is losing his hair, like I have lost. Okay, that what is happening? Okay, so these are the small things. So how does it get manifested is shown over here. So I'll just tell you that when you do normal X-ray diffraction, so this is the geometry we have, which is known as Bragg-Brentano, but like what kind of rays are these? This is parafocusing geometry, right? But I don't use like parafocusing. What I do is I use what is known as parallel beam geometry. And now when I do X-ray, so let's go back to our Bragg's law, and you know that what is going to diffract here? Only these planes, right? They follow the Bragg's law. They are horizontal. They will contribute to diffraction. These planes are not going to contribute, right? So in a polycrystal, this is a very exaggerated thing, but in a polycrystal, not all the grains contribute to diffraction. Here what I have fixed my Bragg's condition. My theta here and theta here is fixed. So I'm going to call it theta b. So I go at a particular Bragg's condition. So now I am not able to see. Okay, it's like if I wear a red goggle, I'm going to see everything is going to appear red to me. Okay, so here I am seeing only at this particular orientations, which are parallel, right? So they are going to contribute to diffraction. If I change the orientation, maybe something else will coincide. That I can do, right? But now what I am going to do is, instead of keeping, so I fix my Bragg condition and I am going to tilt the sample. This is what Professor Garg talked about. So I don't know where I kept it. Oh yeah, so if this is my sample, so here that if the X-ray beam is coming like this and pointing out, going out this way, at a Bragg's angle, which planes are diffracting? The planes which are parallel. Right? So in those grains where the planes are parallel, they are coinciding. But there are grains where the 111 planes, let's assume that we are looking at 111 peak, are like this. Are they going to coincide? No, they won't, because they are not normal. But now, if these are my 111 planes in some of the grains, now if I tilt my sample, what is going to happen? I can come in a situation where now the plane normal and the sample normal coincide. Okay, so this is what I do. I tilt the sample. And that is what I have shown you over here. Let's not forget about this thing. You start from the center and you start tracing a spiral or concentric circles, and you plot intensity. So you are changing two angles. What you do is you are also rotating the sample along phi. This is phi, 4-circle diffractometer, what Ashish Garg sir mentioned. You can do this using 3-circle diffractometer also. So you are rotating the sample and then you are tilting also the sample. So that is why you get polar plot. These polar plots are nothing but your pole figures. Okay, so this is, and because this is not telling you how just which direction is coming out, it also tells you radially if you are changing, how it is oriented. So this is one way you can represent or measure texture. But this tells you information only about 111 planes, because I have fixed my Bragg condition. Okay, and then for obvious reasons, geometry reasons, you know that I can't tilt 90 degrees. Because if I forget about 90, I can't even go beyond 70. Because if I tilt 90, what is going to happen? It's just going to kiss and go out, right? So beyond 70 degree, you can't even do. See, what happens is, your peak becomes, the shape of the beam changes. If it is nice circular, it becomes elliptical, and it is difficult to handle. As you tilt, right? So if it is a spot here, a circular spot, it becomes elliptical. You don't like it. Okay, so you tilt, you get information. You use plenty of such scans, and let's not go into it. And then you measure, so this is what Dr. Kobe showed us yesterday. That in area detector, what happens, that you get a large angle, large view. Here you are having a small view in position sensitive detector, which is linear detector, and scintillation detector is your small point. So you are measuring point by point. So pole figure measurements take a long time. In my lab, or rather in the ACMS lab, it takes us around 6 hours to measure 2 hours for one pole figure. To get one radial plot, it takes 2 hours. And depending on the symmetry, so we work on cubic material, it takes we have to measure 4 pole figures. If the symmetry reduces, how many views you will need, more or less? More views. Okay, so you need more pole figures. So on and so forth. And then there is lot of, so what I want to say is that this is with X-rays, but there are some exotic things available, like synchrotron. In synchrotron, the intensity is so high that you put and you can measure. So this is very good for in situ studies. So Professor Suresh has, or rather you are planning to do some in situ studies in synchrotron, right? So if you are deforming the sample and you want to see what is happening, I showed you in my in situ studies that the grains rotate, there are twins forming and they disappear. If you want to do in situ and measure this texture, you can do it using synchrotron. Or you can use the neutron diffraction. This is what Professor Unger talked about. Why you do neutrons? If your grain size is very large, then or in geological samples people use neutron diffraction only, because the grain size is very large. Okay, very similar things. Okay, so other techniques I won't go. Professor Shekhar will talk about electron backscatter diffraction. So to summarize, texture or preferred orientation of crystallites is not an exception. It is the rule. But it is a language, it's like, French or like Sanskrit, I'll say Sanskrit. Why? Unless and until people say that, the grammar of Sanskrit is like, there is a lot of maths. But someone who doesn't understand Sanskrit, for him or her, it is as good as an alien language. To appreciate that beauty, you have to understand that language. So whenever you learn a new language, there is a whole lot of literature, music, and art form and other things which are existing. Only when you start appreciating that, then you understand it. So so we have to understand that texture. So language and all is very high fun things. But I'll tell you, when I come from Nagpur, so for me sambar was only one sambar. So whatever that sambar masala comes, my mom will make. Only when I went to Bangalore, then I learned that the sambar coming from Bangalore and Chennai and Trichy are all different. So you have to acquire that taste. So you have to learn crystallographic texture, and once you practice it, then you will acquire that taste. Then you will acquire this ability to differentiate and to use it, and to differentiate and kind of exploit it for your own benefit. It is very, very important to see for your electrodeposition thing. So if you can tell me what all you are doing, in anything and everything that you are doing, texture is always there. So, and it affects all your mechanical as well as any physical property it is going to affect. So with this I will come to an end, but I am going to do some advertisement. So the advertisement is, one is for, there is a fantastic, fantastic book by Professor Suhas and Professor Ray. It is now available, so the e-copy is available, but I will also do advertisement of, there is a review which I wrote with my supervisor. This is available online, you just type this out, Gurao and Suhas, crystallographic, or rather Suhas and Gurao, crystallographic texture in materials. This is available for free. You may have to pay for this. And these are like detailed things, but I strongly recommend you go through this review. Means I'm ashamed, I'm a shameless guy, so I'm going to advertise myself. Please go through this review. Please go through this review, and then you can go at least for the library. You ask for this book, because this book is even more fantastic. It is probably one of the most well-written book on crystallographic texture, which is available. Because other books are too detailed. Okay, and with this, I think I will take your leave. Thank you very much for your kind attention.